Okay, this video is on the third law of thermodynamics and a discussion of calculating entropy changes in reactions. Okay, so a quick overview. We've already discussed the first two laws of thermodynamics. The first is that energy is conserved, and the second is that the entropy of the universe increases with a spontaneous process. So the third law of thermodynamics has to do with entropy again, and it is defined as this. Okay, so the third law of thermodynamics states that the entropy of a pure crystalline substance at absolute zero, which is of course 0 Kelvin, negative 273 degrees Celsius, is zero. And if you think about this for just a second, it should make sense. We have discussed that at 0 Kelvin, molecular motion would cease to exist. Well, if that's the case, and particles are no longer in motion, then they would have an entropy of 0, because remember that entropy is randomness or disorder. So if they're not moving, no entropy, and so this law should make sense to us. Okay, so from there, we go into how entropy changes in a chemical reaction. So the first thing we're going to talk about is how it changes during a phase change, or even just during the heating of something, and then we'll talk about chemical reactions. So let's see, we'll repeat ourselves here. The entropy at 0 Kelvin is 0. And it increases as a solid is heated. Following that, we're going to talk about that we have big entropy changes during phase changes. That's kind of a star important takeaway point. So if we talk about this from a graphical perspective, kind of paints a picture in your head. If we look at a graph of delta S versus temp, now I'm going to put two important temperatures on here, which would be the melting point and the boiling point of a substance. I don't really care what those values are, nor do I care who this substance is. I just want to talk graphically about what this graph would look like. So as we've already said now twice today, at a temperature of 0 Kelvin, entropy is 0. So I should have a point here at the origin. So then if I take my substance theoretically at 0 Kelvin and I raise its temperature, well, obviously it would be a solid, but the entropy would increase because I'm giving heat, kinetic energy, to the particles, and those particles are starting to move. So I would see an increase in my entropy, something maybe like this, until it gets to the melting point, where then at the melting point, when we do a phase change from solid to a liquid, and liquids have much more entropy than solids, my increase in delta H is very large. Okay, it goes up very, very quickly because of the phase change. And then the same thing's going to occur again. Once I melt my substance completely and I'm only then heating my liquid, yes, the entropy will go up, but not as much. So this slanted kind of sloped line, and that will continue to happen all the way up to the boiling point, where again, when you vaporize that substance's entropy is going to increase dramatically. And then, of course, the gas could increase as well. So this graph might remind you of a heating curve, right? The one where we talked about temperature stays solid during a phase change, and except it's kind of like tilted 90 degrees. But that's a graphical discussion of how delta S changes as temperature increases, or of course you could talk about how it changes as temperature decreases, and that would be if you were coming down this graph. Okay, so that's your basic overview of how entropy changes with heat or with a phase change. And then now we're going to talk specifically about something called standard molar entropies. And they get this not symbol, right, that little degree symbol, which means standard. And we've seen this before with delta H. Okay, so the standard molar entropy is defined as the entropy value for 1 mole of a substance in its standard state at 1 atm and 25 degrees Celsius. And we look up these values in the same chart where we looked up delta H's of formation. So I inserted a picture here, and that would be this chart. So if we look closely, before we had only used this column for delta H, now we're going to be focused on the S column, okay, for all of these substances, which is the entropy value. Notice the unit joules per mole times Kelvin. So just like delta H, these values are for 1 mole, meaning if we have 2 moles, we would have to double that value. Okay, so a couple observations about these values that kind of compared to when we did delta H of formation. If you can remember, delta H of formation was the energy required or released when that substance is, 1 mole of that substance is formed. And a lot of these values were 0. Like take, for instance, this first row. Solid aluminum delta H of formation was 0. That's because aluminum's a solid element in its standard state, and it takes no energy, nor does it release energy because it's already formed. Okay, so that was where we learned delta H's of formations for elements, and diatomics is 0. However, that's not the case. Look at aluminum solid for S, right? It has a value. Well, that's because everything will have some amount of disorder. So that's our first point. Oops, I'm down here. Our first point is now that unlike delta H of formation, entropy does not equal 0 for elements in diatomics. So be careful making that assumption like, oh, it's 0, like we used to make for delta H. That's not true for S. Second thing to think about is that your S values are going to be positive because everything has some disorder. So I'm just going to group this in with number 1. There is an exception. I think on the chart there is one that's negative. I'm not sure why, and we're not going to discuss that. So we're going to go from the standpoint that all S values are positive because everything has some amount of randomness or disorder. Something we've already talked about is that the entropy of a gas will be larger than the entropy of a liquid, which will be larger than the entropy of a solid. And you could prove that to yourself by looking at some of the numbers in the chart. A third point and a fourth point, these are kind of tied together to consider about the entropy value for something, is that entropy tends to increase as molar mass increases. And the fourth one, we'll kind of discuss these together, is that entropy tends to increase as the number of atoms increases. And we can do a quick discussion of these two kind of rolled into one by looking at, I'll just go back to the chart, looking at aluminum solid versus aluminum oxide. Let me pull these two numbers. So aluminum solid is an entropy of about 28 and aluminum oxide is about 51. Let me write that down. Okay, and so kind of 3 and 4 tied together. This shouldn't surprise you because 3 says the entropy will get higher if the molar mass gets higher. Well, this definitely has a larger molar mass than this. Notice its entropy is higher. And then the same thing for 4, that the number of atoms tend to make entropy be larger. And again, this one has 5 atoms, this one only has 1, so this has a larger entropy than just the aluminum by itself. So that's kind of a combination of those two things to consider for entropy values. I'm going to erase that for now just because I didn't give myself enough room here. And we're going to talk about one more thing before we do these practice problems. Okay, so in our previous lessons, we were able to qualitatively predict a sign for delta S. In a reaction, we would say it's either going to increase or it's going to decrease. It's going to be positive or it's going to be negative. But we had no idea how to put a numerical value with that. So this now is a discussion of how do I not only predict a sign, but how do I calculate quantitatively the value for delta S of any given reaction. And I do it using this chart. Okay, and so if you can remember doing this with delta H, it was one of our 4 ways to find delta H, or we called it P minus R. The same thing is going to be true for delta S. Okay, so I now have delta S for any reaction at standard conditions is going to be the sum of the entropy values of my products minus the sum of the entropy values of my reactants. And again, this is what I refer to as P minus R. Okay, a couple things to keep into account. One, it is P minus R, right, the sum. So you're going to add all your products, add all your reactants, and then you're going to subtract those two values from each other. Be very careful, excuse me, with that negative sign. And then the second thing to consider is, again, that these are molar entropy values. So it's per mole. So we'll have to account for that in our balanced chemical equation. So here's to practice. And again, we need our chart to do this. So calculate delta S for the following reaction. So P minus R, here we go. So delta S is going to be equal to the sum of the products. Right? So these two we're starting with first. Oops. Oh, goodness. Okay, so 2 aluminums, I go to my chart. We look up the fact that aluminums is 28.32 joules per mole times Kelvin, but that's per 1 mole, and I have 2 moles. So essentially what we're doing is multiplying this by 2 moles, which is going to cancel the mole unit. I'm no longer going to write that mole unit. I'm just going to reduce my unit to joules per Kelvin because I know the mole is going to drop out when I account for how many moles I have. So that's my 2 aluminums, but then I need to account for my H2O. Being careful to remember that the state of matter matters, right? I have to account for that, and I have to make sure I'm reading the correct S value from my chart. So I have 3 of them, and the water vapor is 188.38. Just kidding, 83. Again, joules per mole times Kelvin, but since I'm multiplying by the 3, I'm just going to go ahead and reduce my unit. That is all my products, and then I'm going to subtract that from my, or I'm going to subtract my reactants from that number, sorry. I have 1 Al2O3, and its entropy value is 51. And I have 3 H2s, who, remember, careful, it's not an entropy of 0. It is 130.58. We do the math, being careful not to hit a wrong button on the calculator, and you can get a delta S value for this reaction. I got 180.39. And we can talk about a couple things here. It's positive. And so most of the time we would go back up to my reaction and we would say, hey, does that make sense? Entropy should be increasing. And you might actually say, you know what? I'm not sure I could have predicted that. And here's why. A solid and a gas, and you're making a solid and a gas. Oh, well, I had 1 mole of solid, but I make 2 moles of solid, but I started with 3 moles of H2 and 3 moles of water. This would have been a hard one to predict qualitatively, meaning just a sign. So with my values here, I'm able to not predict, but to calculate the entropy. I almost said enthalpy. The entropy, it comes out to be positive, which means it's increasing in disorder. That one would have been hard to predict just as a sign without this math. So one more, determine delta S for the synthesis of ammonia from into an H2. Well, that means into an H2RUR. Reactants, ammonia is NH3, as this is the famous reaction we've worked with so many times. Of course, I have to balance. If we don't balance, my numbers are incorrect. And then same thing, delta S, products minus reactants. So I have 2 ammonias. Ammonia is 192.5. And I'm going to subtract from that. Again, these are not 0 because it's S and not delta H. So 1 nitrogen and 3 H2s. We do the math. Negative 198.2 joules per Kelvin is my answer. This one, though, however, I think you should be able to justify why this reaction would be a negative delta S. I'm going from 4 moles of gas to only 2 moles of gas, a decrease in moles of gas, a decrease in entropy, which means a negative value for delta S. So now we know that we can calculate, we can not only predict the sign of delta S for most reactions, but we should be able to calculate delta S for any reaction, provided it's occurring at 1 atm and 25 degrees Celsius, and provided I have the information contained in this sheet. And I would use products minus reactants, or P minus R, to calculate delta S.